Hello, welcome back. With this video we'll start the optical fibers, and in this video we'll give introduction to optical fibers. This is the side view of an optical fiber. We shall discuss the construction, working principle in this video. An optical fiber can be defined as a cylindrical electromagnetic waveguide that operates at optical frequencies. From this, we can understand that the structure will be in the form of a cylinder. It is an electromagnetic waveguide, and the operational frequency is optical frequency. Optical frequencies generally mean 10 power 12 Hz to 10 power 15 Hz. The band of frequencies starting from 10 power 12 to 10 power 15 Hz in the electromagnetic spectrum are generally referred to as optical frequencies. The optical fibers will be very thin, maybe about 70 micrometers. The advantage of an optical fiber is that one can launch light at one end of the optical fiber to receive the light at the other end of the optical fiber with minimal losses. Consider this cylindrical object, the optical fiber, and we are launching light into the optical fiber. At this end of the optical fiber, we are receiving the light at the other end of the optical fiber. We are using the ray theory to explain the propagation of light from one end of the optical fiber to the other. The ray that we launch into an optical fiber will undergo several total internal reflections to reach the other end of the optical fiber. When light propagates through the optical fiber, the losses in the intensity of light will be minimal. Now we shall try to understand the working principle of the optical fiber. The working of optical fibers can be explained using two different theories. One is a ray theory. The second one is mode theory, or it is also called as electromagnetic mode theory. We use the mode theory when the cross-section of the optical fiber becomes comparable with that of the wavelength of the light. Under such conditions, the ray theory cannot explain the propagation of light through the optical fiber. So we make use of the electromagnetic mode theory, where the light will establish certain well-defined patterns of the electromagnetic fields in the optical fiber core. When light is launched into an optical fiber, several electromagnetic modes are excited or established in the core of the fiber. So when we launch light into an optical fiber whose cross-sectional area is very small, it can be comparable with the wavelength, and if it can be comparable with the wavelength of the light that is being launched, then one notices that electromagnetic fields are distributed in different patterns, and each such pattern is called as mode. So several number of electromagnetic modes can be excited or established in the core of the optical fiber. Light generally propagates through the core of the optical fiber. To understand the working principle of an optical fiber, let us recall the Snell's law. Suppose you have an interface. This line separates two dielectrics, say dielectric N1 and dielectric N2. We shall also assume that N1 is greater than N2. Means the refractive index of medium 1 is more than that of the refractive index of medium 2. Suppose we are launching a light to the interface with an angle theta 1, touching the interface at this point, say O. Then the light will enter the medium 2 with an angle theta 2, which will be greater than theta 1, because when light enters from a denser medium to a rarer medium, or a medium with a higher refractive index to a lower refractive index medium, the ray would move away from the normal. This is the normal. So ray is incident and touching the interface at this point. The refracted ray goes in that fashion with angle theta 2. Theta 2 is the angle of refraction, and angle of incidence is theta 1. When you increase the angle of incidence to one particular angle of incidence called as theta c, the refracted light goes along the interface separating N1 and N2, or medium 1 and medium 2. This particular angle of incidence is called as critical angle of incidence. The angle of incidence is equal to the critical angle of incidence. The light would travel along the interface. If you increase the angle of incidence further, then you notice what is known as total internal reflection. When the angle of incidence theta, if it is greater than theta c, that is the critical angle of incidence, then the ray would reflect back into the same medium, and this is what is called as total internal reflection. We make use of this principle to construct the optical waveguide. Now we introduce one more slab below the slab with refractive index N1, which means we have two identical slabs above and below the slab that is made of material 1 with refractive index N1. If we have a ray that is entering this arrangement and touching the interface at say this point, it is making an angle of incidence that is greater than theta c, that is the critical angle of incidence. This ray obviously will undergo total internal reflection. Similarly, this ray also, it is touching the interface at this point and undergoing total internal reflection and touching the above interface at this point. The angle of incidence will be the same as that of the angle of incidence here. As a result, the ray further propagates like that. This type of a geometrical arrangement of dielectrics with refractive indices N1 and N2 is known as planar waveguide. The central slab is going to hold the entire light that is entering into the arrangement, and the central slab is called as the core, and the slab above and below they are called as cladding. Since the refractive indices of these two slabs is same, we may call this as a symmetric planar waveguide. If you look at the refractive index of this arrangement, then it perhaps looks like this. We are plotting the refractive index along the vertical direction. So within the core we have the refractive index that is a constant, and again the refractive index is constant across the clad material here. The graph showing the refractive index as a function of the separation from the center of the core is called as the refractive index profile. On either sides we have the cladding and we have core in the middle and the refractive index along this direction. Since on either sides the refractive index is same, so we call this kind of a planar waveguide as a symmetric planar waveguide. If you can have the core in the form of a cylinder, this is the core, and the cladding all around that, meaning the core and the cladding they are coaxial cylinders, then such an electromagnetic waveguide is called as optical fiber. So you have a core which is in the form of a cylinder, all around that we have the cladding, and over that we have the buffer. The buffer essentially gives the mechanical strength to the optical fiber. The core is generally made of either glass or plastic or any transparent dielectric material. The cladding can also be glass or plastic, and the buffer can be another plastic. The diameter of the core ranges from 8 to 62.5 micrometers. Diameter of the cladding will be about 125 micrometers, and the diameter of the buffer is about 250 to 900 micrometers. In this video, we have started our discussion by stating that an optical fiber is a cylindrical electromagnetic waveguide that operates at optical frequencies. The thickness of the optical fiber will be about 70 micrometers. When light is launched into an optical fiber, at one end of the optical fiber, one can receive the light at the other end with minimal losses. Working of the optical fiber can be explained using two different theories, the ray theory and the mode theory, or the electromagnetic mode theory. We have seen the Snell's law, we have seen the critical angle of incidence, we have seen total internal reflection, we have also seen the structure of a planar waveguide, we have seen the refractive index profile, and we have seen how the optical fiber cross section looks like and its structure. Thank you.